Okay, this will be lesson 4 of chapter 6, and we'll begin by talking about something called the energies of orbitals. We spoke about orbitals last time and how electrons exist in these orbitals, which essentially are three-dimensional graphs of the probability of electron density. A lot of words for just saying where the electron is found. One quick word here, the s orbital is actually filled before the previous d orbital. So usually for the second shell, for example, you have the 2s and the 2p subshells. Remember, the s has one orbital, the p has 3 orbitals. So this is nice, and easy. Here then, in the third energy level, you'd expect us to go from 3s to 3p to 3d, but we are interrupted by the 4s. And you can see this actually on the periodic table. The periodic table shows you this this idea. And we'll see this in just a minute. We'll have to remember that we go to P and then we go to S of the next level and then back to D. A similar thing will happen when we get to the F subshell. So today, or in this lesson, we'll talk about electron configuration, which essentially is a way of symbolically representing how the electrons are filled inside the atom. And the ground state configuration is the lowest energy arrangement. What we mean here is electrons can actually jump to a higher energy state, and then eventually they'll come right back down to the stable state, and that's how they emit their light. So these electrons, for example, can jump to higher states. There are more empty subshells and orbitals out here they can jump into, and then they fall back down. That's kind of the idea. So this notation, hopefully you've seen it before, but just to remember, this big number in front shows you the shell number, also called the principal energy level, which is essentially, remember, shell. That's what we call our shells. This is the subshell, sublevel. The P is the sub-level or subshell. And then the 5 is how many electrons you've got in that subshell. Notice this subshell is not completely filled. P can hold 6, but there are only 5 in there. And if you take a look, this is a good idea to kind of review how the periodic table is set up to reflect the subshells and shells and so forth. So at the very top, we'll begin with the first shell. This is essentially on the innermost portion of the atom. So you've got the nucleus, and you've got essentially these shells, these energy levels going out. So you first go to the 1s subshell, and notice that helium's symbol is right out here with the noble gases. And then you've got the 2s, and then the 2p. After the 2p, we go into the 3s, 3p, and then when we just talked how after 3p you don't not go directly to 3d, but you pass through 4s. Notice that 4s lies before 3d. A similar thing will happen with F. And that's essentially what this n-1 means. The n is the energy level, so here we have energy level 4, so you would expect for it to be 4d, however it's 1 less. n-1, n is 4 here, so -1 gives you 3. For the d block, you have to subtract 1 from your energy level. So notice out here is where energy level 6, usually periodic tables will have the energy levels right out here, like so, at the very left. So, but you'll notice that in row 5, essentially, the D is 1 less, it's 4D. A similar thing happens to the F subshell. In fact, this actually sits right here. So after the 6S, you'll go down to the 4F, and then up to the 5D, as we fill the more complex, the configurations of these more complex elements. And so n-2 signifies that you take your number 6, for example, and subtract 2, and that's you get 4F, and that's where those numbers come from. So why don't we try to do a configuration here. This configuration will be, we'll do 2 of them, one for selenium and one for lead. And for this we'll have to consult a periodic table, so take out your favorite periodic table and we will be able to look at it. I'll actually, here's my one of my favorite periodic tables, nice and color-coded. Not my most favorite, maybe my 7th favorite periodic table. And so I'll be looking at this one. Let's see. So let's begin first with selenium. and we want the full configuration. So technically we want to go from 1s all the way out to selenium. If you take a look at where selenium sits in the P block. Let's go ahead and circle it for our visual pleasure. Here's selenium. And so what we'll need to do essentially is begin at the beginning with 1s and travel all the way throughout the periodic table through these subshells until we get to selenium. That's the idea. So we'll begin with 1s out here with the hydrogen, and as we go along, because it's a little tough to split the screen here, we'll probably have to kind of talk about it and then write it down. So we'll begin with the 1s out here. This is, remember, the 1s, and then we'll go on to the 2s, then to the 2p, 3s, then 3p, 4s, then remember this is the 3d, and then we'll finally finish up with 4p is the idea. And selenium is the fourth element, 1, 2, 3, 4, so its configuration should end up as 4p4. So hopefully we'll be able to see that. So let's go ahead and hit that. So selenium's configuration will begin with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and finally 4p4. And we'll say that's at the end there. So this is selenium's configuration. If we do the same thing for lead's configuration is going to be a bit longer. So taking a look at the periodic table, find lead, you'll find that lead is right here. And for lead, we'll have to go through the F block. Remember, this portion of the F block sits right in here on the periodic table. So we'll have to go through the F block here. And technically where we left off, for selenium, we'll keep going. We'll keep going this way. This will be 5s. This will be 4d, 10. This will be 5p, onto 6s. Then we'll go on to the 4f. After we fill the 4f, we'll go up to 5d. And then we'll finish up with, this will be 6p. And lead is the second element in the P block, so we'll say 6p2 is where we'll end up. So let's go ahead and mark that down. So we got, I'll go ahead and do down here, so we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, this is where we go into the D, so we got 3d10, then back to the 4p6, then 5s2. After 5s, recall that after 5s, we got 4d, so we got 4d10 onto 5p6, then 6s2, and here's where we get into the F. So just as a recall, let's recall that. So notice after the 6s, we'll go into the 4f. So we got 4f, and the F subshell can hold 14 electrons. So 4f14, then back up to 5d10, and as we said, 6p2. And this would be lead's configuration. Hopefully not too bad. Okay, let's talk a few minutes about something called the exceptions to the order of the filling. And if you take a look at copper, so take a look at copper on the periodic table, what you'll find is that copper actually has, copper sits right here. You should expect copper's configuration to be, this is, remember, 4s2, and then 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9, because it's the ninth element in the D block. However, if you study copper, what you'll see is its true configuration is 4s1, 3d10. What happens is an element gains more stability if it's able to have a fully filled D subshell. So a fully filled D subshell will get it more stability, and the way it does so is actually it moves one s electron into its D. So this is true for copper. It's also true, by the way, for silver. which is also in the same position. It's also true for gold. So for each one of these, for silver, for example, the 5s electron, one of these electrons, will jump in and fill its d. So you get 5s1 and then 4d10 instead of 5s2, 4d9. A similar thing happens to chromium. If you take a look at chromium, chromium actually sits as the fourth element in the d block, and again, elements gain stability if they have a half-filled subshell. So this will be the half point of the d subshell, because you got 1, 2, 3, 4, 5 elements here and 5 more. So it'll try to be like manganese. It'll also send one of its s electrons into the d to get a half-filled d, and that's exactly what you see here. Instead of 4s2, 3d4, one of the s electrons will jump into the d subshell and get 4s1, 3d5. So, and a similar thing will happen also to molybdenum and tungsten as you go along here. This note down here says that these anomalies are not restricted to the d block. The f block also, the f block atoms have quite a bit of these anomalies. So these guys down here. In fact, I think I have a periodic table. Yes, we do. So if you take a look as we're filling these, say take a look at this portion of the periodic table. So you see we got we're filling the 4f, so 4f6. Then we got ourselves 4f7, and then you'd expect it to be 4f8, but it is not. We fill 5d. We put a 5d electron in, and then we go back and get the d back into the f. You don't have to memorize any of the d or any of the f block anomalies or exceptions, but just know that they are there. On the web sign, if a web sign asks for an element like europium or gadolinium in this case, realize that it may not follow the simple filling rule. There may be an exception. So neptunium, notice, has an exception as well. So just be ready for this. And the further down in the periodic table you go, the more this happens. And the reason we do this essentially is because that's how nature did it. And science for us is essentially figuring out what nature did and explaining it. So we're not making this up. Nature is the way. This is the way nature has done it. Okay. And next, let's talk about the noble gas notation. Turns out for elements like lead, which is pretty far down in the periodic table, the electron configuration is pretty long. So there is a way to shorthand it, and especially because most of the inner electrons are not involved in any sort of bonding and any sort of emission of light, and we only care about the outer electrons. We're going to actually ignore the inner electrons, and we'll do so by using the noble gas that comes before the element in brackets, and then we'll add the whatever's left, the outer configuration. So why don't we take a quick look. If you take a look at phosphorus, its full configuration is 1s2, 2s2, 2p6, 3s2, 3p3. This is a phosphorus configuration, but what you'll find is that this portion of phosphorus actually belongs to the noble gas neon. Neon, having 10 electrons, will have 1s2, 2s2, 2p6. If you follow it on the periodic table, you'll see this is neons. So we can substitute, instead of writing this out, we'll just put neon in brackets. Again, this is because these are inner electrons that will not be involved in any sort of chemistry, so we can actually safely put them inside of neon. These, however, will be involved in chemistry, so we want to leave them out here. So whatever follows neon then we'll write until we get to the full configuration. Again, the inner ones are called core electrons or inner shell electrons. The outer ones are called outer shell, also valence. This actually is very important. We'll be dealing with valence electrons a lot more. These are the electrons involved in bonding, and therefore in chemical reactions. Okay, so why don't we do the two elements that we wrote full configurations for, selenium and lead. Why don't we do the shorthand version of the configurations? And then let's consult the periodic table. There he is again. And so recall that selenium is right here. And so what we'll do is we'll first have to find the noble gas that comes before selenium. And that noble gas, if you go back across the periodic table, you'll actually hit argon. So argon will be our noble gas that we'll use. So we'll have to put argon in brackets, and then after that, whatever follows argon until we get to selenium. What follows argon here, remember this is 4s, This is 3D. This is 4p. So we'll get 4s2, 3d10, and 4p, 4 again, like we've done before. So for selenium, its noble gas configuration will show argon, and then, as we've seen, 4s2, 3d10, and then 4p, 4. So just like predicted, and that should work. Let's do a similar thing for lead. Looks like for lead, for the second one, if we take a look at the periodic table, lead is actually right down here again. The noble gas before lead will be xenon, which sits out here. And then after xenon, we'll have 6s. Remember, we'll have 4f, 5d, and then we got 6p with the 2, because it's the last one. So let's go ahead and put that down as well. So for lead, we've got xenon, then we got 6s2, then remember we go to the 4f, 4f14, 5d10, and 6p2. So notice it's quite a bit shorter, and a little more, you'll retain a little more of your sanity as you're writing these in the noble gas configuration. Not all of it, but most of it. Okay, and then we'll finish up with talking about something called orbital diagrams. In the electron configurations that we've just shown, we show subshells and electrons, but we do not show orbitals. Remember the p subshell, so say if your shell 3, p subshell holds 6 electrons, we don't see in here the orbitals represented. We see the shell represented, the subshell, and the electrons, but where are the orbitals? And we have a different way, another way of representing orbitals called orbital diagrams. The simple way of doing this is beneath each subshell or sublevel, we'll draw lines, squares or lines, usually I'll do it in lines, and then we'll place arrows as a visual way of representing electrons. And we'll actually also indicate the spin. So this is a much more detailed representation of the electron filling. And here this is Hund's rule is actually very important. And it says that do not pair up until all the orbitals in the same sublevel have 1 electron. And I'll show you what this means, but this rule will actually be very important to follow as we go along here. So if you take a look, these are orbital diagrams. So here's the electron configuration of carbon. Carbon has 6 atoms. You got 6 electrons. You got 1s2, 2s2, 2p2. So for the 1s subshell, there's 1 orbital. For every s subshell, there's 1 orbital. For the p subshell, we have 3 orbitals. And notice these 2 electrons are placed. So these 2 electrons are essentially placed right in here. And notice we don't put them together up and down. This would be the incorrect way of doing it. If you had the box to put up and down, this is the incorrect way of doing it. You have to first spread out the electrons among all the orbitals before you double up. And this is because of the repulsion between electrons. They will not go into the orbitals until everyone is half filled. Very similar to how students get on the bus in the morning. You usually find an empty seat, and then when all the empty seats are gone, then you reluctantly decide to share a seat with the pimply young freshman. Okay, so why don't we draw some orbital diagrams. Let's pick phosphorus and silver. Silver is actually going to be a little in-depth. It's going to be down there. So this is actually a perfect opportunity to review a little bit of the F block filling. Actually, we won't have to get into the F block with silver. So again, take out your periodic table. Oh, and here's mine. Let's first do phosphorus. Here's phosphorus. We're going to do noble gas notation. Again, we don't really need to show the inner electrons as they will not be involved in any sort of interesting chemistry. So we'll begin with neon. Here is our noble gas. And we'll essentially write out the configuration with the orbital lines beneath. Remember, this is 3s and this is 3p. So really, there's not too much to deal with here. So let's go ahead and do phosphorus. So for our noble gas is neon. We'll put neon in brackets. And then after that, we'll do 3p2. I'm sorry, 3s2. Get the s first, so 3s2, and then 3p. And it's a good idea to spread them out a little bit. Why don't we do this? Why don't we spread them out? That gives us a little more room. And then remember, phosphorus is the third element in the p subshell. So you get this sort of thing. Then we draw lines. Here's where it's different. So for every s subshell has one orbital. That gets one line. Every p subshell gets 3 lines. And then we're ready to fill in the electrons. We've got 2 electrons here and 3 electrons here. So let's fill each subshell separately. Well, first, why don't we do a different color for your visual pleasure. We'll do an up-spinning electron and a down-spinning electron. For the p subshell, we'll have to put all the electrons as up-spinning. The incorrect version would be to do this sort of thing. This will actually be incorrect. So this would be for phosphorus. Not too bad. Let's go ahead and do the same thing for our second element, and that in our case will be silver. And silver looks like is right down here on the periodic table. So what we'll do is krypton will be our noble gas, and then we'll go into 5s and 4d. We'll finish up with 4d. So let's go ahead and go back. Let's get silver in there. So we decided that for silver, we're going to use krypton. Put krypton in brackets. And then after krypton, you got yourself 5s2. And then you got 4d9. However, this is, there's an exception. If you recall, there's an exception to filling silver. Silver sits in one of those exception positions. So what we'll do, we'll ask one of the electrons to jump into the D. So actually we have 5s1, 4d10. And then every s subshell has 1 orbital, every d subshell has 5 equivalent orbitals. So let's go ahead and fill them in with electrons. We have just one arrow here, and we get 10. So make sure you fill it in as all ups first, 1, 2, 3, 4, 5, and then come back and put the down electrons. And this is the orbital diagram for silver and phosphorus. Notice you'll see the orbital breakdown, and you'll see the electron spinning. What you can see here is actually a little more detail. You can see something called unpaired electrons. This right here is what's called an unpaired electron. And the reason this is important is because this electron can pair up, can team up, and can bond with another atom. Through this, there's an empty, think of it, there's an empty spot right here. That's why this is unpaired electron is important. Idea is important. Okay, and that looks like it. So this will wrap up lesson 4 of chapter 6.